Yes, join. You are the resource person. You are not sure. You make you ask him to explain.
So you can just push this side. Then when your processor.
Sir, you sit, sir, here. Sir, you come, sir.
Start? Yes. So start. You want me to start or what?
I will start.
No, Vinay, you why don't you sit? I'll just introduce. Okay. From where? Yeah?
Here.
No problem. Dear friends, colleagues, offline participants and online participants, I welcome you all for this national workshop on computational linear algebra and graph theory. Every year, in the month of December, we used to have some or other activities like ICLA series of conference or some workshop, other workshop, or some other thing. This year, thought of doing something like that again, and I just asked two of my colleagues. One was my former student, and the other one is my colleague at MIT. Dr. Vinay, please. Dr. Vinay, assistant professor at, am I wrong?
Yeah, correct.
Okay, assistant professor at MIT, mathematics department, MIT, and Dr. David Raj Michael is assistant professor at, correct me in case I go wrong, Vellore Institute of Technology, Chennai. And they readily agreed to formulate some course for you and decided to have workshop in this 3 days duration, 18 to 20 of December. And I left all the responsibility on them, and he requested Professor Kunjam Sham Prasad to give the facility, and he also readily agreed. And Professor Harikrishnan, PK, they are with us, and they have given all the support to us to organize this. And maybe Vinay will give you the overview of the activity and continue with this particular short session of inauguration. This is very informal, and immediately after that, your technical session will start. Please, Vinay.
So in this 3-day workshop, we'll be covering, as the title says, linear algebra as well as graph theory. We'll do little bits of theory as required. So what do you plan to cover in linear algebra?
Yeah, I have linear transformation, vector spaces, and then decomposition of matrices, and little bit of graph neural network whenever time permits. So as the time permits, actually we'll go a little higher, and as the audience is actually required more, then we'll give more. So that's the plan. Otherwise, basically the plan was just linear algebra, vector spaces, matrices, and then elementary forms of them, decomposition of matrices, and the corresponding applications in currently what's going on in data science, image processing. So that was the plan on the linear.
Yeah, so thank you. We will integrate that with and make it hands-on, integrate that with the Sage Math software and make it a hands-on session. So only very little theory as required. Most of it you already know. Right, so we'll be seeing how to use Sage Math to do all these computations. Okay, it is not just numerical computations, symbolic computations also. And on the graph theory side, again, we'll start with the basics. So how to define graphs in Sage Math, how to construct standard graphs, custom graphs, then all the parameters associated with graphs, matrices associated with graphs and little bit of spectral graph theory as well as algebraic graph theory, including graphs defined on algebraic structures and such things. So we'll be doing it with theory plus tutorials. So we'll first have a theory session, which is demonstration from our side. And then after that, we will have a tutorial session where you yourself can explore whatever is taught and really internalize what we are doing. Thank you. Yes. So now I request our HOD Professor Shyamprasad sir to brief about this.
Thank you, Vinay. And first of all, like to congratulate Sir Founder Karams for these activities. It really helps the student, and most of the students are joining online, and some of the students joining offline. It's a good scenario, and this training helps not only to give your research inputs, but also how the computational aspects goes along with the theory. So normally we expertise in theory and you learn theory subjects, but the computational aspects lagging behind, and these are very much essential for the present contemporary needs. So every research, if you have a computational aspect, then it gives you a lot of weightage, and this platform really helps you for bringing out the computational aspects. So I wish you all the best, all the participants, offline and offline, online and offline participants, best make use of this facility and the learning resources. And I especially thank Dr. David and Vinay, resource persons, for giving their patience and training to all of you. And they are really reachable all the time, even if after the workshop also, they are always helpful. I know from many years. I wish you all the best. And I also thank Hari Krishnan for supporting this and coordinating the event. I also thank Uma Shankar all the time. He is also with us. Thank you one and all, indirectly, directly supporting this. And thank you for this opportunity where we feel like this is an opportunity to organize here. Thank you very much, sir. Thank you.
So now we request Dr. Hari Krishnan to actually give us a few words and also to announce about the activity that we have on the last day.
So good morning, everyone. So I hope that everyone will enjoy the 2.5 days computational linear algebra and graph theory workshop handling by Dr. Vinay Masun and Dr. David. So I want to just announce a small program that we are planning to organize it on the last day, 20th of December. And we are all aware about the Ramanujan's birthday on 22nd, since it is coming on Sunday. So we are planning to conduct it, celebrate it just 2 days before. That we are planning to arrange it on 20th afternoon. And we will have a talk from 2 to 3 by Dr. Kalyan Chakrabarti. He was a former professor in HRI Prayagraj and former director of Kerala School of Mathematics, and currently he is the professor and head of SRM Chennai. And he will be giving a talk on a brief journey and life of Ramanujan. And all of you are invited to attend that talk. And the talk will be delivering through this same link what you people are attending this particular workshop. So all are invited to attend that one. And at the same time, I wish you a good learning experience from this national workshop on computational linear algebra and graph theory. Thank you.
Thank you, sir, for your words. And, thank you, everyone present here, as well as the dignitaries. So we will now begin with the sessions. Thank you. Thank you.
Let's say. Okay, thank you.
Okay, good morning, everybody. The things are settled down, then we'll start. We'll turn on the videos over here. So we'll start in 2-3 minutes. Just set the things up so that we'll get started. Is everything okay? The online participants also, if you have any doubts, you can probably unmute yourself. I think
They can raise their hands outside.
they can raise their hand.
Always.
Okay. Okay. So then you can post your questions in the chat, or you can raise your hand so that we will allow you to unmute and then you can ask the questions. I'm talking about online participants. Offline participants, obviously, you can raise it like this and we'll answer your questions. So we already have talked about. Oh, sure. Yeah. So I already have multiple peoples to help you out. We have obviously Dr. Vinay, we have Uma Shankar, and we have Magesh, and we have also Krishna for any technical support. So if you have any clarification during the session, you can ask them immediately. They will actually come and help you. So what I assume is you already have installed the Sage Math. Is that so? Yeah. So have you opened the Sage Math? Like, can you tell me what is 2 plus 3? Don't tell me right away like that. Just put in Sage Math and then compile it. Is it actually telling you 5 only or not? So if you're using a Jupyter notebook or Jupyter Lab or something, then in the top right corner, you will see that there is a Sage Math 10.5 or whatever the version that you have installed. Yeah. How to evaluate. You see, the way actually now I have run this cell is you can see that there is a play button over here, right? Yeah. If you hover over it, it says run the cell and advance. That means what it's going to do is it's going to, if I click on this, and it's going to also run the cell and it's also going to move to the next cell. The cursor is going to move to the next cell, so I can right away actually start working on the next cell. That's the idea. There's a shortcut to do that as well. If you press Shift and Enter together, and that does the same job, whatever that button was doing is. Everybody comfortable now? Okay. Is everybody ready? Please raise your hand if you're ready. Shall we go ahead? Yeah. So hopefully the online participants are all also ready. I have one chat message. Yes. So if the online participants are also ready, please can you put a message in the chat group saying yes or no? Let's see. I believe the audio is also okay. Yes, good, very good. The audio is correct, right, Krishna? So then we are good to go then. Okay, it's already 9:30. We should start. So my plan of covering it is just on and off, like go to board and then meaning writing it in the in my iPad as well as coding it simultaneously. So that's how it works. So if you have pen and paper, probably you keep it along the side so that we'll start writing it as well. Okay, so that's it. Now in Sage Math, I'll cover the programming part, whichever required as and when we need it, because this is not a dedicated workshop for Python programming or Sage Math. So generally, Sage Math is just a wrapper which is around a Python, meaning the Sage Math is actually built on Python. So anything, whatever you can do it with Python, you can do it in Sage Math for sure. That means literally any library that is available for Sage Math, you can bring it. We can bring it inside, and you can go ahead and then work like say Python itself. Then why is a Sage Math? Because Sage Math is actually built on top of Python. It offers so many other flexible functions like what we wanted for a mathematics perspectives or a statistics perspectives or any operation research person's perspectives. Like I can literally define a vector just like this. For example, if I say V is equal to, I'll zoom it a bit so that it's clear, and also probably put it in full screen. Yes. And I think I can. Yes. Is that a little better? So if I right away say that actually is V equal to vector, and then the vector is just a array of numbers what we have. So the way that we represent an array in a Python environment or in Sage Math environment is just putting a square bracket surrounded by them and then write whatever the numbers you feel like. Okay. So then that's a V. And if I just simply say V, then it is like this. Okay. Right away. So now you can see, first thing what happened here is it has been considered as a vector in a mathematical sense. It's not been considered as simply an array of vectors. That means I can do so many other things like I can multiply this vector with other vector. I can add this vector with the other vector. I can do a dot product of these vectors. So many other things, whatever you can do it with specifically to a vector, you can do it. For example, whether I want to check whether a vector is actually completely contained in another vector space or not. Such things are possible over here, where the Python is actually not able to do so by default. Okay. For everything, actually, you have to write a very large functions in Python. However, Sage Math, actually, I have done all of them in hand and then specifically designed for mathematical perspectives. So that's the idea. That's what we are here. And it's also very helpful for any research perspectives because in research, what we want to do is mostly like, let's say we do not want to have this vector. If right now, actually, if you look at the type of this V, it says it is under a module called vector integer dense. That means what? Actually, right now, it is considering this vectors as an integer vectors, meaning the module which is corresponding to that is an integer module. Okay. In Python, it is not so. It is usually generally considered as a real number only. Like let's say if I did 3.1 extra along with that, now you see that the module has changed. I reran both cells right now. So what is the module right now? Now it says actually it's a free module and it's under the generic dense class. So actually what is happening here is this has been now considered as a real number field. Okay. Now I can specifically tell it to consider to some other field as well. For example, a vector can be defined it like a vector and then if I write double R like that, now this will be considered as a real vector. Okay. Now what and all I can do is that I can now actually consider this as a rational vector like that. Now you see, I think probably I should take this and then I'll make the first one is RR itself as it is, and then I'll do a type over here, and then better I'll do the type here. So the first one is just a real vector field element, and the second one is the rational vector field element. Do you see the difference? That means who is this 3.1s and how is the 3.1s been considered? That has been considered as just simply 31 by 10. It is a real number. It is a rational number. That's how it has been considered. It's never been, it's never a now floating point number now. Yeah. Hopefully it's clear for you. So that flexibility is there in Sage Math. Like you can change the corresponding vector space from where that vector has to come up. Okay. So that's the beauty of Sage Math, and that's why we use it. And there are multiple other things as well. Probably we'll go ahead and then find out what's going on and all of them. So before that, probably we'll introduce what is the vector space itself, and then we'll go further. So we know what is a vector, right? So what is a vector? It's just simply an array of numbers. Now, probably I have some tutorial sheets along with me. So I will share it with you. You can anyway actually have it in your hand and then practice in the tutorial hour. Anyway, for now, I'll just for giving you comfortable zone, I'll create a vector v1, and then I'll create another vector v2. Let's say 5, 6, 7, and 8. Okay. Now I have both of the vectors are 4-dimensional vectors. That means they are all part of the R4, correct? And then now what all I wanted to do was I wanted to probably just add these two vectors. Yeah. So I can do v1 plus v2. That's now clear, I guess. It's 6, 8, 10, and 12. It's just addition of it. I can also multiply a vector and then find out the other vectors like that. We call it a scalar multiplication of a vector. Now you see this 2 is getting multiplied with every element in the vector v1. And we can also do a scalar linear combination of the vectors like this. It's just 2 times v1 plus 3 times v2. Same thing. Whatever we do it in the hand, and we are able to do it here as well. Yeah. So when I do an addition, obviously we can also do a subtraction as well, correct? Now we can also find, I should zoom it a bit. This. Let us start. Yeah. So if I had v1 dot norm, and that gives me the norm of it. Now remember, actually, what is given here is square root of 30. It is not some floating point number. So there is a real calculation is going on now. That means all these vectors are, as I told you, if all of these numbers are integers, then what is happening? That is considered that the vector is actually part of the integer module only, rather than a real module. Okay. So if I have to specifically tell who is that, let's say, for example, RR, that means actually you have to consider that as a real number. Then it is actually considered that as a real number. You can see that the numbers are now changing into some floating point arithmetic, right? So by default, if I'm not wrong, it is 17 bits. You can actually 17 bits is actually equal to, I don't remember what is the number of decimals. 17 bits is equal to, I think, some 10, 12 decimal places. So bits is actually slightly different. And 25 bits, like that, you can change the approximations as well. So by default, it is always 17 bits, that I'm sure. Now, if I give v1 dot norm of, now it's no more square root of 30. Rather, it gives me the exact number up to some decimal point corrections, right? So it is now 5.477. That's the beauty of Sage Math. Everyone is convinced now? All of you are doing it along with me, or should I go a little bit slow down. Yes, sir. Square root of 30? You did not get it. That's probably the vector. What you have created is actually having some real number. Is this the way you have created? Then you will not get square root of 30, no? Because now square root of 30 has been converted into a real number now. If you keep the square root of 30 as square root of 30, then that's just an irrational number as it is. Okay. So if I change this vector field from where that vector has been chosen, if I, let's say I change it to QQ, which is the rational field. Okay. How does it say? Can you tell me the number? I'm not running it now. The online participants can post the answer in the chat box. Is that fine? What's the answer? If I change the vector field into a QQ. Yeah. Now V1 plus V2 itself automatically, first of all, changed into a real rational number rather than the real numbers. And then obviously the linear combination has become a rational number. And then the norm is now again back to square root of 30. Because I do not know what to do with the square root of 30 because I am in the rational field. Rational field has no way of dealing with square root of 30. We write square root of 30 as square root of 30. Okay. So what else you may wanted to probably do it with the vectors? Maybe you wanted to dot product V1 with V2. Now again, this is also is actually pertaining to what you have actually defined in the vector field. If I would have defined the if I would have defined V1 and V2 or the vectors from a real field, then the computation is with respect to that real precision. If I would have configured for a rational field, then it is the computations are all rational numbers only. That means if I say 1 by 3 plus 4 by 3, then if I compile it, it is always pi by 3. If you run it as a real number, then it is never going to be 5 by 3. In other words, it's going to give me something what is actually real numbers for 1 by 3, what is actually real number up to some decimal places correction, and then add those decimal places correction and give me a number. So the real calculation doesn't happen over there, right? So it's just only always approximation. But here, what is happening over here is a real calculation. It's a good thing happens. Because in research, we do not want an approximation generally. Whenever we wanted a real calculation to happen, then we wanted the real calculation only to happen. Not an approximation over there. Yeah. So that is the point. Now you also would have done something called as an outer product. We call it as cross product of two vectors. And you know that how does that cross product works? This is the problem. Type error. Cross product is not there. Cross product only defines for vectors of length 3. Yes. You know what is the problem. The problem is actually the cross product is defined only for length 3. So you really have to actually define vectors of length 3 only. So V1 is vector, let's say 2, 3, 4, and V2 is a vector, let's say 1, 2, 1. Now V1 cross product with V2 is -5, 2, 1. Okay, fine. So all of you are a little bit comfortable with Sage Math now. So shall we just probably start introducing vector space, and slowly we'll look into it, revise it, what we have done, and then we will come back to this Sage Math again. Okay. Yeah. I don't know, for some reason I'm not getting the screen mirroring option. Vinay, can you? Huh? Yes, you're handling it. Okay, good. Sure. Okay. Just I need the Wi-Fi because I need to connect it to the hotspot. No, not the hotspot. On. Yes. Thank you. So without the Wi-Fi, my mirroring will not work. So, is it clear in Zoom? Anybody is watching in Zoom? Whatever is visible there is there. Okay. Okay, so we'll slowly start with actually the theory little bit, and then we will go ahead with that. So first of all, what is a vector space? I'm not going to write all the axioms, so I'm going to just probably skip it, and then I'll simply say a vector space V over a field F or K, whatever it is an abelian group. I'll assume the group at least. And the moment I say abelian group, the addition is already defined. And with or equipped with scalar multiplication. Remember, the scalar multiplication is defined in this fashion. So you take a scalar and you take a vector, and then you try getting a vector back, correct? So that function should be defined such that this additional property should be satisfied. What is that? That distributivity on vector addition. We need a of x plus y to be equal to ax plus ay for all a in the k and x comma y in the v. Yeah. So that what first property. The second property which I need is, and I need the distributivity of scalar, the vector over the scalar addition, right? So this is also ax plus by, and this should be for all a comma b from the field k and any vector from b. Okay. Then we also need that 1 dot v should be equal to v for all v from v. Now this 1 is the multiplicative identity in the field k. So that's clear for you. Now the k can be anything we want, meaning any field whichever is actually having any characteristics is actually going to work for us. So what do I mean by subspace then? So any vector space which is sitting inside another vector space with respect to the same addition, with respect to the same field, it's going to be called as a subspace. Yeah. There is a characterization for subspace. We can actually first of all verify all the properties, whatever is there except the closure property and the existence of identity. Everything else is going to be called as a parent property. That means if that is there for V, then for any subset of V, all those properties will be satisfied. No need to be a subspace as well. So if it has to be equipped as a subspace rather just being a subset, then all that we need is just an extra additional properties of just closure property. Yeah. So what we will say is for all x comma y in the W, and A belongs to the same field where the V is a vector space over with. If suppose AX plus Y belonging to the W, then clearly what we say is W is a subspace. Yeah. Yeah. So additionally, probably what we need is 0 must belongs to W. That's the only thing we needed. Yeah. So you take any scalar, maybe a small problem you can solve. Take any scalar you have, maybe or any scalar set of n vectors, n values. I'll call it as n values. So simply a1, a2, and so on up to an, which is subset of the field k.
and define W, which is contained in Kn, such that the x1, x2, and so on up to xn vector will belonging to the W if and only if summation over I ai xi is equal to 0. So what I'm doing here is I'm trying to find a linear combination of vectors, and I'm trying to say that this set W is actually a subspace. And subspace of whom? Subspace of whom? Obviously, Kn. You can easily prove, first of all, some results. What about the intersection of two subspaces? If W1 and W2 are two subspaces, whenever I say simply subspaces, then I mean that they are subspace of a specific vector space, and the W1 is also subspace of that, W2 is also subspace of that. So all of them are assumed. So I will not exclusively tell W1 is subspace of W, W2 is also subspace of W. So when I say W1 and W2 are two subspaces, I meant the W1, W2, both of them are subspaces of one single vector space. Yeah. Then these questions we can ask. What about W1 intersection W2? It's clear that both W1 and W2 has identity 0. Therefore, W1 intersection will W2 will have a 0. What about the closure property? Like if I have two vectors x comma y belonging to W1 intersection W2, and you take any scalar a from k, do I have confirmation about ax plus y belonging to W1 intersection W2? Yes, why? Because I know both of the W x and y belonging to W1 and W2 separately because they are in intersection. And therefore, ax plus y, first of all, must be belonging to W1 for sure. And similarly, ax plus y must be in W2. Therefore, together, this says ax plus y must be in W1 intersection. So identity is there, closure is there, and therefore, W1 intersection W2 is a subspace clearly. Any doubt in that? It's clear, right? What about the union? If you have two subspaces, do you have the union also as a subspace? Yes. If one is contained in the other, clearly yes. Because the larger one will become the union, correct? Otherwise, it's not so. It need not to be true. For example, if you look at even a subspace in R2, a very standard example, you take an x-axis, that is a subspace first of all, clearly, because any number you pick up from here in x-axis, you add them, then those two numbers will have an addition over here somewhere, correct? Or in the left side, that's the only difference. So x-axis is subspace in R2, and similarly y-axis is also a subspace in R2. But what about x-axis union y-axis? Whether x-axis union y-axis is a subspace? Yes or no? Little bit doubtful. I'll verify. First of all, I just need to be checked as a subspace of R2 again, correct? So I just have to check two properties. One is actually identity is there, and yes, 0 is there. What about the closure property? So for the closure property, I just have to check whether the addition of two vectors belonging to the same vector space or not, first of all. And after that, only I have to check the scalar multiplication. How do I do that? I know one special property of vectors. If you look at vectors, for example, you take any vector over here. Let me change the color. You take any vector over here. You take any vector over here. What will be the sum of those vectors? Where will that be? Where will that be? Geometrically, it is a diagonal of. Geometrically, what does it mean? It is a diagonal of the parallelogram actually is formed by this, right? So you take a parallelogram, which is over here is just only orthogonal. So the parallelogram is just simply the rectangle only. So that vector will lie over here. However, where is this vector? This vector, is it there in either x-axis or in y-axis? Neither of them, right? You take any two vectors, this is the property in x-axis and y-axis, correct? So therefore, x-axis union y-axis will never form a subspace. So therefore, W1 union W2 need not be a subspace. Yeah. As you said, the other way around is if one of them at least contained in the other, obviously that becomes a subspace. Just because if W1, let's say, if without loss of generality, I assume that W1 is contained in W2, then clearly W1 union W2 is actually equal to W2 itself. And therefore, since W2 is subspace, and therefore W1 union W2 is subspace. Okay. So it's not just only true for two elements. So if you try to write the result, then you take any intersection or meaning the arbitrary intersection itself, not just a finite intersection of vector spaces. Take any arbitrary intersection of vector spaces, and that also forms a subspace. Arbitrary intersection of subspaces forms a subspace. So this is a subspace. Okay, I'm making it a little bit shorter, otherwise I have to keep writing it subspace of whom, etc. I believe that is understood. So what we know for any v given for any vector v in V, let's say you define something called as kv, which is defined as a times v for all a in the k. Meaning you look at all the scalar multiple of v and then form it as a set like this. And now this set is clearly a subspace for sure, subspace of subspace of V, clearly a one-dimensional subspace of V. I'll tell you, of course, I did not introduce what is the dimension yet so far. However, this is going to be generated by a V. So that's what I'm saying. So I'm trying to say that this V is going to be called as a generator of V, a generator of this KV. Yeah. Now I can actually extend this subspace. Like I can now take two vectors. So for any u and v belonging to V, now probably I'll call that as K, and then in the set actually I will write it like this, K, and then in the subscript I'll write u comma V, and that is actually equal to you take any A into U plus some B into V. This is true for every A and B in K. Now this gives you a linear combination of U and V. Now this is also a subspace of V. And who are the generators? U and V, as long as they are unique, correct? So I'll also assume that U is not equal to V. In fact, I will assume that U is not equal to some alpha times V for any V. It's not just I expect that to be unique like that. I expect that to be at least not at all having any linear combination to happen to with U at all. Okay. So then U and V will become a generator for this set, right? Yeah. Now remember, we call this as a line. Technically, this is what we call it as a line. In fact, that's a line passing through origin. So you can also specifically write that is a line passing through origin. Well, probably the other one actually we can call it as a plane, and specifically plane passing through origin, etc. And three-dimensional subspace passing through origin, like that. It keeps going. So you can generalize this construction. So by generalizing this construction, of the vectors of line or vector lines of any of a vector space. So I am now defining a line for a general vector space. You take any vector space, now you know what is the line over there. Like a vector space of matrices, you know now what is the line over there. So any property which is hold for a line, you can try verifying it whether that is true or not. In fact, obviously that is also going to be true. Yeah. Okay. That means now I can talk about the intersection of two lines, intersection of two planes in any any generic manner over any field I want. Yeah, that's the good thing. So what do we have now? So by generalizing this construction of the vector lines of a vector space, we can choose any set S of vectors. Now I'm even actually relaxing the factor of actually having one of them is not a linear combination of other. That's not required for a generator set like that. And now consider the set of all linear combinations. The set of all linear combinations of the elements, I'll call it as S here, of S. That is what I'm calling, what I'm actually looking at. I'm looking at A1 V1 plus A2 V2 plus and so on plus AN Vn plus and so on. Of course, I do not have any limit there, such that all this AI belongs to K for every K. Yeah. Now it's clear it's a subspace, right? We have already verified this, I think 2 times already now. So this is going to be a subspace. What I will also call here is this space, I will call that as a span of V1 and so on up to Vn and so on, actually, because I did not restrict it to some finite linear combination system. Okay, fine. So now I have so many elements in my hand. So sometimes actually V1 may be exactly equal to V2 or sometimes some other linear combination of other. So how do I restrict all of them? Because they are not going to be so useful when I am actually trying to discuss with the vector space in general. So how will I actually restrict them? So there comes something called as linear dependence. Without telling this name, I already introduced it, but anyway, at least we'll do that now. So what do I mean by linear dependence? Anytime I say, for example, I take a vector u, and then I say that vector is actually some alpha times v. That means what do I say? I say that if I look at the geometry, what does it mean? That means I have a vector u which is somewhere here, and then vector v is somewhere here, and then u is simply it just actually on the direction of v itself, and just sitting on top of v. Yeah, it's just little larger or shorter. That's the only difference. So such a vector, we are going to call it as a dependent vectors. They are not actually dedicatedly telling anything special about the vector, because I already know that if I know a vector, I can generate a line out of that vector. That means anybody else can be easily caught using that vector. So I'm not really bothered about the vectors which are actually going to be in the same direction. So I wanted somebody else to perform something good. So technically, I'm just going towards how many vectors, how many different direction vectors I needed for a vector space, because taking every vector in a vector space and then dealing with them is going to be cumbersome, because obviously there are infinitely many vectors in a vector space. So dealing with all of them is not easy. So if I have to really verify a vector space properties, or if I really have to verify a property is being hold for a vector space, then I really have to check for everybody in a vector space, which is definitely not possible realistically, meaning verification through computer is also not possible. So at that time, what we need is we really need somebody called as representatives, and we'll verify with them. If that is actually hold for that with the representatives, then it is assumed that it is actually going to be hold for everybody else. So that's where we are going ahead. Therefore, this linear independence has been defined in this fashion. So how it has been, why do I call it as first of all linear? Because you see, you can write this as u minus alpha times v is equal to 0. That's the idea. Yeah. Now, you know, this are actually is in linear in the variable u and v, and just linear combination of u and v. In other words, there is no multiplication of vectors happening over here. Therefore, technically, if you look at the corresponding polynomial expression, you take this as x and then they take this as y, then this becomes a linear equation. Therefore, it's linear dependence. That's all. So how will I say actually three vectors are linearly dependent? That is very simple, right? Now, because I know that now I have the concept of having linear dependence like this. So what I can say now, we take three vectors now. So v1, v2, v3. I'll say these three are linearly dependent if one of them is a linear combination of the other. Minimum, right? At least. So how do I say one of them is a linear combination of other? Now, you know, if one of them is actually written as some alpha times beta times this, now I know I can bring this alpha and times beta, v2 and beta times v3 to the left side. And that gives me, I can say something like this. If alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to 0, and if this people has to become a dependent, then what should happen? At least one of these alphas must be non-zero. Yeah. So if this happens and at least one of the alpha is, or alpha I is non-zero, then what we call, then we call or we say the set v1, v2, v3 is linearly dependent. Okay, that's technically saying not all these three vectors are required. I just need only two vectors. As if now I can generate the next one. Yeah. There's also a possibility that only one vector is required. Still, we do not know. Yeah. So then when do we say actually linearly independent? Very simple, no? If it is not dependent, right? If the vectors are not dependent, then automatically it becomes linearly independent. That means what I am saying, that is, I am trying to say, let's say I have alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is equal to 0. Then if at least one of the alphas are 0, then it has become linearly dependent. Now I am saying that is not true right now. That is not true means what? Nobody can be 0. That means this will imply alpha 1, alpha 2, alpha 2, alpha 3 is equal to 0. So if that equation becomes 0 and that says that alpha 1, alpha 2, alpha 3, all of them is 0, then we say v1, v2, v3 are is a linearly independent set. Hopefully that's clear. Okay. So now that I have a linearly independent set, therefore now I can try reducing the people in the span automatically, right? Because they are so many now. I already noticed that if you and we are actually sitting on the same line, having both the vectors and then try generating the vector space, or having only one vector and try generating the whole line, it's going to result the same thing. So trying to now come down to a place now. So if you have an R2, then I know who are the people who can be linearly independent. Now I know, let's say we call 1, 0 and 0, 1. So these two people are now enough because I know anybody over here, let's say A, B, can be now written as A times 1, 0 plus B times 0, 1, correct? And therefore anybody, any other people in the R2 can be expressed using 1, 0 and 0, 1. Then obviously what's happening, meaning that means actually this says the span of the set 1, 0 and 0, 1 is actually equal to R2, and therefore we don't need anybody else. Okay, because of the this property, and this happens by default for any vector space. So I can actually generate for Rn automatically. I believe don't need to write that, you know. So on 0, 0. Yeah. Okay. You can do the same thing for any vector space as well. Like for example, you have a now. By the way, actually, I call this as a standard vector space. Sorry, standard basis. I sometimes also call this as ordered standard basis or standard ordered basis, whatever feel comfortable. Why I call this as order is because I have a specific order to generate these people, or I have a specific order to write these people. There is nothing like, we do not have any partial order or something. It's just ordered in a particular fashion. Yeah. So for that reason, I usually call this fellow as E1, E2, E3, and so on up to En. So for example, you have a vector space M2 of R. What is M2 of R? This fellow is simply a set of all matrices of order 2 by 2. Okay. A, B, C, D, such that A, B, C D can be in any field you want. Okay. Then what's the basis of this? So basis B of M2 of R. Okay, I have written R here, so this is also supposed to be R. Yeah. Probably I'll write K so that I can write K here. Yeah, M2 of K. So B M2 of K. Who's that now? So this is actually is going to be equal to 1 0 0 0, then 0 1 0 0, then 0 0 1 0, and then 0 0 0 1. Now, without any shame, I will call this fellow also as E1, E2, E3, E4 like that. Yeah, I have no shame. And this is also ordered in a particular fashion. Just assuming that actually is all this vector can be looked at 1 0 0 0 like that. Use the same order. Yeah. Now, similarly, you also have, if you look at like for example, if you look at any K, okay, and then generate a polynomial in X whose coefficients are all in K. So this is going to be look like this. So it's going to be like A0 plus A1X plus A2X square plus and so on. So I'm not restricting anything, like degree need not be less than or equal to somebody else. And where all this AI belongs to K for all K, for all I. Then this is actually is going to be called as a polynomial ring or polynomial vector space. Yeah, it's called as polynomial ring in general. And it also happened to be vector space. If you verify all this vector space property, it will handle. Now, can we try finding the basis for this? Actually, we can write a countable basis though, but the problem is actually we will not be able to count and complete it. So it's just infinite, but countable. Yeah. So you can write that as 1x square and keep writing until the end of your life. That's it. 11, no? It's 10:30. Oh, like that. Oh. So we'll break in 5 minutes then. Okay, after that. So this is a basis. But if you suppose, let's say, we usually denote it by Pn of x, I guess. That's how everybody does. So this is actually equal to, you take an, a0 and so on, a1x and so on up to an x power n. I restrict now the polynomials from polynomials whose degree is less than or equal to n. Less than or equal to n. Yeah. Obviously, if you take a polynomial whose degree is equal to n, will that be a vector space? Why is not? Because if you look at even difference of two polynomials of same meaning, you take any polynomial of order n like this, whatever you want, just like that. And then you take another polynomial, just take it as a monic polynomial, then obviously you very simple subtraction will prove that this is the resultant is no more a polynomial of degree equal to n. So obviously, polynomial of degree equal to n is not going to be a vector space. But otherwise, the polynomial of degree whose degree less than or equal to n is always going to be a vector space. Okay. Fine. So far, whatever we have seen is, we have seen one great thing. Of course, what we will do is actually we'll verify it in the Sage math. These are the questions that we wanted to probably look at. That I know there are vectors in my hand and I can generate a vector space out of those vectors. But given a vector, can you check or can you Yeah, can you check whether, let's say we call this fellow V, whether V belonging to some subspace or not. So that we do not know how to do it, and then probably we'll do that after the break. And then we also know now, we know how to generate a basis for vector space right now. We just keep adding the lines again and again, then automatically what will happen, actually it generates the basis for the whole space. Now, do you have any other spaces? So do you have, first of all, any other basis? Or in Word, actually now we'll call that as a better basis. Just simply colloquially, we'll try to call it as a better basis. And what do I mean by better basis? All of them actually depending on application. So for a particular application, if the basis is suitable, then we'll call that as a better basis. So why do we need all of them, and how do we generate all of them? Or in other words, if I suppose I know that any vector now can be written as, any vector can be now written as a linear combination of a basis, correct? Now question is, suppose if I have a basis, if I have a another basis, if I have another basis, so how do I write that? How do I write the vector using that basis? Now this is very important because in data science and other disciplines, what they want to do was, they wanted to do something called as a PCA, or principal component analysis. And what is that means is, you have a basis, you have a vectors which is written in a particular basis with respect to one basis, and you try converting those columns into another basis. Therefore, I will get a better view of the data. In other words, I have a better control of the data, so-called. We want to look at the variability of the data is actually in one axis or two axis or three axis, and how does it works, all of them. So such things actually is coming under finding out something called as a change of base matrix, and using that, how do we actually find it out? Okay, we will discuss all of them. Maybe 11 o'clock. We'll start again. Yeah. Okay, so in another 10 minutes, 10, in fact, 15 minutes we'll give at least. Yeah. So in another 15 minutes, we'll start that. We will have the tea because tea has already arrived. We're supposed to break it by 11, I guess. Huh? Online participants are, I believe they are listening already. So online participants also having the 10 minutes break. Please grab coffee or tea at your home. Let's come back by 10:45. Yeah, so 10:45 we'll start again.